Hey, hey, happy Friday, everyone. Welcome back to Markov Chains. Um, Always do that between my intro and actually starting. Um, Homework 8 is out and it is it's a little long. I don't actually have an opinion yet on whether it is long, just looks like it has an additional problem. But I was specifically asked about problem 1. So I want to talk about that really. It's a quick problem, so we'll talk about it really briefly. Problem 3 is tricky and unlike all others, so I just want to give you some hints on that. And problem 6, we will be talking about how to do that today. So you shouldn't know how to do that. I mean, you could do it, some brute force method, but so let's talk about problem 1. I need to share my screen. So problem 1 on the homework. On homework 8, on problem 1, so I was asked for some hints on this, and it's really a lot easier than you would have imagined. It's also not the problem that I'd meant to put down, but we'll do it. So we have customers arriving to a single station queue in accordance with a Poisson process with rate lambda. So there's a server or station, and they're coming in according to a Poisson process with rate lambda. And assuming exponential service times with rate mu, we want to find the birth and death rates for this system. And it's a little bit different than in MM1 because there is this probability that customers will turn around. I mentioned the idea of balking in the past, and that would be something like the input process has rate lambda. And so if it had rate lambda, this is not the problem yet, then if there's 0 people in the system, the rate until the next arrival or birth is lambda. If there's 1 person in the system, the rate until the next arrival or birth is lambda. But if I have balking, then that is some sort of like if the number of customers in the system is greater than some fixed n, then people are going to start leaving with some probability. So let's say that's a probability P. The arriving customer, or let's say he'll stay. So the arriving customer will join the queue with probability P, otherwise leave. Now, this is a simpler case than what's going on in problem 1, because in problem 1, the probability that they join the system is system dependent. It's not constant, which is probably more realistic if they join a big line. But if this were the problem, then the birth rates would be up until n would just be lambda, and then lambda at if there's n plus 1 people in the system, now the arrival rate is going to be thinned out to P times lambda. Like people are going to be coming in less often. So you've got your Poisson stream coming in and some of them are turned away. So if you kind of thin that out to the probability ones, the people who will join, that's what's going to happen here. Coming in at a fast rate, and then once the line is big, they're coming in and leaving. So the ones that actually arrive are coming in at a slower rate. So what I had meant for problem 1 is for this probability, this bulking, to happen only when the line got long. But instead, I have all the customers just like, I don't know why I'm here. Customer arrives and there's 0 people in the system and they leave, but they do because I have, instead of P, I have alpha, and it is dependent on the number of customers in the system. So what we have is, so for problem 1 on the homework, the arrival rate when there's 0 people in the system is the Poisson process arrival rate of lambda, but it's thinned out because some of those people just turn around for some reason. It makes no sense in this problem because I didn't have a limit on I didn't have this sort of cutoff, but the arrival rate is going to be lambda times alpha 0. That is kind of the thinned out a fraction of the total rate. And so that's the slower rate that people are coming in than they are if you include all of the people, the ones that turned around as well. And lambda 1 is, so when there's 1 person in the system, at that instant, what is the rate of arrival? Well, it's a Poisson arrival rate, but when there's 1 person in the system, they are choosing only to join with probability alpha sub 1. So this is lambda alpha sub 1. And yeah, so it doesn't make sense for people to leave unless they left something at home, I guess, when the queue is short. And the rest of it, there's a pattern. The muse should be easy. This is a very short problem once you understand what it's saying. Okay. I want to talk about problem 3 because it is, I think, the only problem on here, aside from the grad problem, that is not a birth and death process. It is the lattice one with particles, and particles are jumping. Not a birth and death process, but it is a continuous time process. And we want to find a stationary distribution. And how can we do that? Because we're not going to be able to use our lambda 0 up to lambda n minus 1 over mu1 through mu n formula, because it's not a birth and death process. It's just not even the right state space. Here's what's going on in problem 3. We have 12 lattice sites arranged in a 3x4 grid. And they're labeled, and it doesn't really matter how you label them. Maybe this is 1, 2, 3, 4, 5, etc. And we have 5 particles. So the particles are hanging out on different sites. So maybe there's one here, there's one here, one here, here, and here. And so that is a configuration, like one element of the state of the system right now in this picture is that nodes 2, 4, 7, 9, and 11 are occupied. And the states of the system are just going to be all different ways you can choose 5 distinct numbers out of 12 and write them down. So there's really no difference. If these represent the nodes that are occupied, then there's no difference if you change the order. So if I were you, I would start out by saying, let's tie these down and make sure they're always ordered. So I want to look for the stationary distribution of some pi I1, I2, I3, I4, I5, and let's say we're going to assume that I1 is less than I2 is less than I5, because saying that there are nodes 2, 4, 7, 9, and 11 is the same thing as saying they're at nodes 7, 2, 4, 11, and 9. Okay, so going back to what I was saying is we want to find this stationary distribution, and this looks hard. It's 5-dimensional. And that seems hard. Definitely not like a birth and death process. We don't have anything that increases by 1 unit or decreases by 1 unit. So I would look at the rates. So look at I'm going to put this in quotes because it's not going to be how you write it, the Qij. The Qij, the I and j are 5-dimensional. So if you have Q and we're starting at the state 2, 4, 7, 9, and 11, and you want the rate of moving to 1, 3, 7, 10, and 11, that's not going to happen in one instant of time, because when the current state of the system looks like the picture I've drawn, we've got these 5 yellow particles racing to move, and they were exponential with rate 1. So the time the next particle moves is in an exponential amount of time with rate 5, and only one can move at a time, or we get into the little O of H stuff. So the rate here, where I have kind of like very different 5-dimensional states, is 0. The only rates you have to be concerned about is when there's one difference. So something like Q 2, 4, 7, 9, 11. And let's say that the particle on 4 jumps to 12. Only one of them can jump. So that would mean we'd be going up to 2, 7, 9, 11, and 12. And that would have a non-zero rate. The rate of change of the system from this to this would be the rate of movement of this particle to this guy. And I don't have to look at the minimum of 5 things anymore, because the only way to go from this state to this, it's not to have any one of the yellow ones jump to 12. It's to have this one particular yellow one jump to 12. And this one particular yellow particle jumps after an exponential amount of time with rate 1, but he may not jump to 12. And he's equally likely to go anywhere. So jumping to 12 is sort of like thinning out the possibilities where he's going to jump to. And there's 7 places. So we have to split up that rate of 1 into 7 pieces. And so my claim is that this rate is 1/7. It's really 1/7 times the 1, the rate for the exponential rate 1. But then we have to kind of thin it out and say, okay, particle on site 4 is jumping. So like the exit there is almost like a Poisson process with an exponential time to the next event. But he may not go to 12. So we have to consider he could go to this node or this node or this node. He's got 7 to choose from. So he only goes to node 12 with 1/7 of that rate. Now, I still haven't told you how to do the problem, but does that make sense? You don't have to unmute, but please unmute if you have a question, or put it in the chat. Nice, thanks. All right, so we want to find a stationary distribution, and you know, we just computed this 1/7, and this particular configuration didn't matter. It's just that this one, relative to this one, has to be different by only one number. So we can write down every Qij. A bunch of them are 0, and a bunch of them are 1/7. So I would look at reversibility or detailed balance. If you can find a pi that satisfies this, then you've got a stationary distribution. So these Q's are either 0s or 7s, and or 1/7. So I would think about the 2 different possibilities you can get here. A 0 on one side, a 1/7 on one side, and then like the combinations. But I would use detailed balance or reversibility to try. And it's going to be, once you sort these numbers out, it's going to be guessable. And we'll talk about it more on Monday. But I wanted to give you this start because it's very different than all of our other problems. Okay. I know I said the first thing we do today is pasta, but let me just get out problem 6. And this is not a waste of time. Like I'm spent all the time going over the homework. This was a topic I was going to cover today anyway. We're going to derive a formula for this kind of thing that's being asked in 6. So I won't talk about 6 in particular, but what I'm about to do directly applies to problem 6 on the homework. So suppose we have a birth and death process, and we have birth rates lambda I and death rates mu sub I. We have a birth and death process with birth and death rates. So there's a whole collection of them. So I'm just going to put it in brackets, lambda I and mu I. I guess maybe I should say respectively, but it's a whole collection. I don't know. You know what I mean, I hope. So I'm going to let Ti be the time starting from state I that it takes for the process to first enter state I plus 1. We're going to find right now a recursive formula for the expected value of Ti's. And then if you go to problem 6 on the homework, you are given some lambda i's and some mu i's, and you want to determine the expected amount of time to go from state 0 to state 2. So in a birth and death process, you can only move one at a time. So in order to go from 0 to 2, you have to go from 0 to 1. And then you have to go from 1 to 2. And that journey may involve trips back to 0. But the answer to problem 6 is the expected time it takes to go from 0 to 1, plus the expected time it takes to go from 1 to 2, which again, this excursion might take you back to 0, but that's okay. If we can compute an expression for this, the expected time it takes to get to 2 from 1, it will have taken into account the probability that we go back to 0 in the first place and in the first step. And so we're about to derive a formula here that basically you can plug numbers into, because this is the answer to 6. Okay, we know, and it's going to be recursive, we know that the expected time, so now I'm not talking about 6 anymore, just in general, if there's 0 people in the system, the expected time until it jumps to 1 is going to be an exponential amount of time. We showed that birth and death processes, or more generally, continuous time processes on discrete state spaces must have exponential inter-event times. And so we have to wait an exponential amount of time with rate lambda 0, which would make the time 1 over lambda 0. So T0 is supposed to be the time we jump up to 1, and this is exponential with rate lambda 0. And so this is the mean of that exponential. It's easy for part 6. You already have one of these. Okay, so now I want to get a recursive equation off of that. So I want to find, in general, the expected value of t sub I. And we'll see that it's going to be written as a function of the expected value of t sub I minus 1. So you can always use this to find the expected value of T1, and you can use that to find the expected value of T2, and that to, and you can go as high as you want. So this is our goal right now. And I'm going to find this expectation by conditioning on what happens in the very first step. So we're currently sitting at state I, and in the very first step, we either move up to I plus 1 and it's over in one step, or we move down and we have to kind of start again. So I'm going to say the expected value of Ti is the expected value of Ti given the first move from I is to I plus 1 times the probability that the first move, probably didn't need all these words, from I is to I plus 1 plus the other one, and then I will have I to I minus 1. So I'll have the expectation and the probability, but instead of going I to I plus 1, I'll be going down. There will have been a death. All right, we know these pieces. The probability, so given you're at I and that it's greater than 0, the probability the first move is I to I plus 1. The current rate of birth is lambda I, and the current rate, sorry, yeah, that's true. And the current rate of death is mu I, and those are exponentials. And the time to the next event has rate, so time to next event is an exponential with rate lambda I plus mu I. And you can think of this, even though it's going up and down, you can think of like if every time it goes up and down, you mark off the time point where it changes on the x-axis. And that is a Poisson thing with this kind of, well, not really. The rates are changing. Sorry about that. But remember our bugs jumping in our Poisson processes? At the time you're at I, the rate to the next move is lambda I plus mu I. And the probability that you move from I to I plus 1 is just the proportion of the birth rate to the total rate of movement away from I. This is just like the thinning and stuff that we did back with the bugs. We said, well, yeah, I guess I don't want to drag that up.
That I to I plus 1 supposed to be an I minus 1?
Oh, this is yeah, that's so good. This is a bullet, not a multiplication.
Oh,
So I just
okay.
kind of started over. Yeah. Yeah, I don't know what to do. Call it a square. I don't know. But yeah, to I minus one, that's going to be mu I over lambda I plus mu I. So the probability the first move is from I to I minus one is going to be the death rate over the total rate of change of this thing. So that's 2 out of the 4 things that I need to find the expectation, because we had a conditional expectation times a probability plus another conditional expectation times a probability. So those are the 2 probabilities. So let's look at the conditional expectations. Let's look at the first one. What is the expected time? So I'm starting at I, that's given. What is the expected time to move up to state I plus 1 for the first time, given the first move is from I to I plus 1? This is just, since we're going up in the first move, this is just the expected time until the first move, period. So if someone says in the next move you're going up by 1, what is the expected amount of time for that to happen? It's just the time to the next move. You already know it's going to go up. And this is going to be when the current population size is I. You could think of people, right? You could think of I people racing to give birth and I people racing to die. But this is going to be 1 over lambda I plus mu I, because Ti is, and Ti has packed into it a starting at I and going up by 1, because it kind of feels like I should be writing some sort of conditional notation here. But Ti is exponential with rate lambda I plus mu I. When you're at I people in the population, oh, no, no, no. No, 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 that's so wrong. But if you're at state I, the time until the next move is exponential. So the thing inside the expectation that I just squared off, that is exponential. So this is exponential with rate lambda I plus mu I. We're just waiting for something to happen. Lots of things are racing. We have one more piece to get to our conclusion. The expected value of Ti given the first move is actually a death. First move is I to I minus 1. So we're not hitting I plus 1. So first we have to wait for that move that's not helping us get to where we want to be to happen. So this is going to be the mean time until the next move. We're at state I. The next thing that can happen is a birth or a death, and whichever one comes first is what will happen. And so we're racing with birth and death, and the minimum of the birth process and the death process has an exponential amount of time in between with rate lambda I plus mu I. So that's just expected time to the next move. And I'm sure that's confusing because I have EXP meaning several things. And now we're starting over down at I minus 1. So we want the expected time starting from I minus 1. Now we can't go from I minus 1 all the way to I plus 1. We can only move 1 at a time. So we're going to have to move back up to I and then try all over again. So this is the expected time to go from I minus 1 to I. And then finally, this is the expected value to go to I plus 1 from I. So if I put this all together, it's a huge mess. Let me just state this once neatly. We've got the expected value of the time until the first birth, until we go to one individual starting with 0. This is 1 over the birth rate when there's 0 people in the population, because that's going to be an exponential amount of time, and the expectation or mean of the exponential is 1 over the rate. Then we wrote the expected value of Ti. I'm going to write this a little more compactly as the expected value of Ti given the first move goes from I to I plus 1 times the probability that the first move goes from I to I plus 1 plus the other way around. The expected value of Ti given that the first move goes from I to I minus 1 times the probability the first move goes from I to I minus 1. And believe it or not, we've computed all of those pieces. I'm going to plug them in. I'm going to spare you. It's really messy. And once you plug in everything over here, you're going to have expected value of Ti terms and expected value of Ti minus 1 terms. Like this alone was this. So you're going to have these sorts of things in there. So then you just want to, solve for the expected value of Ti. So an hour later, you have the expected value of Ti is 1 over lambda I plus mu I over lambda I times the expected value of Ti minus 1. We have a formula. We know the starting value, and you can use the formula because this is kind of long. But for problem 6, you just want the expected value of T0 plus the expected value of T1. Formula in a box. Okay. So let's talk pasta, finally. The pasta property. This is important for simulation. As you probably already know, or maybe not, I've never formally written it down, but I've said it at least 3 times. This stands for Poisson arrival seed time averages. And if you want to see like the original, when the original discovery of pasta and maybe a more complete proof than what we're going to do here, which is sort of going to be a little kind of wavy, but at least intuitive, then it is in a 1982 paper by Ronald. I know his name's Ronald. I think his middle initial is W, but his last name is Wolf with 2 Fs. And the title of the paper is exactly this: Poisson arrival seed time averages. And what does it get for us? It's something really important for simulation. So it says, the pasta property says the following. It says that arriving customers see the state of the system. Oh, I didn't even give you a setup. This is usually used for queues, but it could be used for really any kind of stochastic system where the arrivals, the external arrivals, are a Poisson process. And they need to be independent of what's going on. For example, with the balking idea in queuing, that means that there's a Poisson number of arrivals, but people are saying, the line's too long, I'm leaving. So there's not really a Poisson number of arrivals. It's no longer a constant Poisson process. It's going to be changing depending on how many people are in the system. But if the arrival process is a pure Poisson process without any sort of dependence on what's going on in the system, let's just think of an MM1 queue, although this is not at all restricted to queuing. So I think I need to set that up before I can say this. We have some kind of continuous time Markov chain on a discrete state space, on a discrete space, and we have the external arrival process. Why do I say external? Think queuing models. If you can leave one server and come back and get back in line, or you can go to another server, that can be considered an arrival to a server, but not an external arrival to the system. So we have the external arrival process is a Poisson process that is independent of the current state of the system. Now I'm ready to state pasta. So pasta says that, I already start writing this? No, I did, but I erased it. Pasta says that an arriving customer sees the system behaving the same way as an external observer who's looking at it at any arbitrary time point t. Arriving customer sees the system or sees the same system, the same behavior of the system. I'll get this sentence finished. You watch. The same behavior, it's not going to be a good sentence though, of the system that an external observer sees at any time. The heck does that mean? Any arbitrary time. This will hold even before I'm just going to talk about when we're in stationary mode. The system has reached an equilibrium, but this actually does not say anything about stationarity. So this could actually be when the process has not yet reached stationarity. But let's say it's stationary. So at any time you want to look at that chain, not a randomly defined time, that depends on what's going on in the chain, but just like pick any fixed t, you look at the chain, and if it's in equilibrium, the probability you see n customers is going to be what we've been calling pi n, the stationary distribution. So I'm being so sloppy here. We're in stationary mode. At any time t, the probability that there's n people in the system is pi sub n. I want to compare that to an arriving customer. So I'm going to do it this way. Maybe this will make more sense if I actually start writing the math. I'm going to let x of t be the number in the system at time t. So when this reaches an equilibrium, we should get our stationary distribution. So the like the limit, we haven't really ever written it this way, but the limit as t goes to infinity of the probability that x of t is n should be that pi n. However, if you start in stationary mode, you'll be there right away. Okay, and this is for never mind. Think queues, think queuing models. In fact, think MM1. I'm going to let NT be the Poisson arrival process, which really doesn't make sense because a process is a whole group of these, but I think you know what I mean. So let's consider the limit as h goes down to 0 of the probability that x of t is n. So I'm not taking the limit in t. So I'm not actually getting to stationary mode. T is some fixed time. And I'm looking at the probability that the number of customers in the system is equal to n. And I'm going to look at it just before an arrival. So someone's walking in to get online, and what they see in front of them is a number of people. And the probability that they see n people, I'm claiming, is still pi sub n. So the Poisson arrivals see the stationary behavior. So I'm going to compute this conditioned on the number of arrivals at time t plus h minus the number of arrivals at time t is 1. This is saying that we are really looking at the system here, and it is just before the person comes in, instantaneously before, because this interval is shrinking down to a length of 0. And yeah, so we're shrinking that down. So if we write out this conditional probability, just using the definition, we'll get x of t equals n, and n t plus h minus nt is 1 over the probability. And so this is just a definition of conditional probability, blah, blah, blah. And then I'm going to use conditional probability, unravel it to rewrite the numerator. So this is the limit as h goes to 0 of the probability. I mean, you could go directly to this. This is 1, given that xt is n times the probability xt is n. I'm always debating at this point whether paste is going to be faster. I don't think so because I'm so clumsy with it. So here's where the Poisson process being independent of the current state of the system comes in. There's just a Poisson arrival process, and they're not making judgments based on the system about whether or not they're going to arrive. What's going on here does not depend on the current number of people in the system. So what I'm trying to say is that this is, the circles make no sense, that this is exactly the same thing as the limit as h goes down to 0 of the probability. I get to drop this, is what I'm trying to say. Yeah, let me not even write that. I get to drop that because the arrival process really has nothing to do with the current state of the system. And once I drop that, then I can cancel this probability with this probability, and we end up with the limit as h goes down to 0 of the probability x of t is n. And there's no h there, so this is just the probability that x of t is n. This is the probability for the continuous time system. And if you let t go to infinity, that's actually pi sub n, the stationary distribution. And what I started with was the probability that an arriving customer will see n people in the system. So the number of people in the system at time t is n, given that the t I'm looking at is exactly one where there's an arrival in the instant after t. And that proves pasta. That's saying that the arrival customer is seeing stationarity, right? So this probability given the arrival is just after t, is the same as this probability, which is not dependent on the point of view of anyone. Does that make sense? Not important, really. The use of it is more important for this class than the proof. But here's how you could use it, and it's a big tool in simulation. So if you have some kind of queue, you would not do this with an MM1. But say you wanted to know the stationary distribution of something complicated, a complicated network of servers that does not have a known closed form expression. One way you can simulate this process is you can say, okay, I'm going to start with 0 people, and then I'm going to simulate an exponential amount of time with rate lambda. And at that point, I'm going to increase by 1. And then you want to simulate an exponential amount of time with rate lambda plus mu because that's the time of the next event. So the next event could be a birth or a death, and whichever one comes first is the next event. And the minimum of those two exponentials is exponential with the sum of the rates. So, you know what I should say before this, the total inelegant brute force way to do this is to say, I have one person in the queue, I'm going to simulate their service time, and I'm going to simulate the next person's arrival time, and I'm just going to see what the next event is, which one happens first. But a much easier way to do that is to just simulate the exponential amount of time until the next event. And then you know you can figure out the probability you go up by 1 is lambda. All the lambdas are the same. There's no lambda i's. Lambda over lambda plus mu. And the probability you go down to 0 is 1 minus p. It's mu over lambda plus mu. So Method one of simulating is actually to throw out a sequence of birth and death times or exponential times, and then do the race. Where you are currently, look at your next arrival time and your next departure time, and whichever is smaller, that's the move that's going to happen. But a better way to do it is this, what I just wrote down, which is just to figure out the time of the next event and then assign it to be a birth or a death. And an even better way to do it, actually, this depends on what you want. If what you're looking for is the stationary distribution, that shouldn't be time dependent. It's like a limiting distribution, which is definitely not time dependent. That's when time goes to infinity. So I claim that we know now, if we believe pasta, we can simulate this in a different way. We can look at the embedded chain, I'm gonna call this the embedded pre-jump. I do call this personally the embedded pre-jump chain, but that could be confused with something else. So I'm gonna say pre-arrival to be more specific. Chain. When you embed a Markov chain, that means you have a continuous time process and you are looking at it only at some discrete time points. So let me draw an MM1. At some random time, it goes up by 1. At some random time, it maybe goes up. At another time, it drops down. At another random time, I go up, blah, blah, blah. This is a continuous time process, and we can talk about the probability that it's in state 1 or 2 or 3 at time t. But if you decide to just grab the value of the process just prior to a jump, so this point 0, not point 0, the point I've drawn, which is at level 0, and just here, just before it jumps, 1 jumps up, which is why I was specifically saying pre-arrival chain as opposed to jump chain, because usually in Markov processes, people consider jumps up and down. So just prior to an arrival. So the next time we have an arrival is over here. And just prior to that, the process is here. And the next time we have an arrival is over here, And just prior to that, the process is here. So this is 1, that's not 1, and this is 2. And so what you're seeing here is that we have like a discrete, we can discretize it at these times. We can say the first value here is 0, and then at time 2, we are at 1. And in this picture at time, not equals. In this picture at time 3, we are also at 1. And at time 4, we're at 2. So we're discretizing the process and we're picking our points very carefully. And then we're thinking of it as a continuous time thing. So you know how to deal with this kind of chain, because now we're back to discrete time. Actually, this one isn't easy to write down. I'm going to show you a different example. This is hard to write down. I wanted to write down the probability. You go from some I to some J, but the problem is that even if I'm talking about going from, there could be many moves in between. The probability in any one step will go up by 1. I can do this. I can do this. Probability we go from I to I plus 1 is lambda over lambda plus mu. And the probability we go from I to I minus 1 is mu over lambda plus mu. And the probability we go from, I guess the probability we go from 0 to 1 is going to be 1. I started talking about a different discretization. This isn't quite right because I can go from 0 to 0 for sure. And that would be like starting at 0 over here and here. So that would be x0 equals 0. And then the next point in the process is still 0 if you look just prior to the jump. So I can definitely stay flat, like move from I to I. All right, so let's say I wrote these probabilities out correctly for a discrete state space and discrete time. Then we can find the stationary distribution for this time embedded chain using our old methods from the beginning of the course. And we will find that the stationary distribution is actually the same as the one we found using the continuous stuff and the Kolmogorov equations. So that was from continuous stuff with rates. But once you realize that if you discretize it this way, if you can correctly write down the transition probabilities, then you can find the stationary distribution the old way. Using the equation ij is the sum over I of pi I, pij, and you will in fact get that pi n is equivalent to what we get in the continuous case. So Poisson arrival C time averages means that for the purpose of simulation, you could not really worry about time at all, and you could simulate this process. And if the process corresponds to where this process is just prior to each arrival jump up, then Costa says it has the same stationary distribution. So if you're trying to simulate it to find the stationary distribution, you can ignore continuous time, which is awesome. Wow, I'm out of time. There are other places where you can embed the chain, and I just wanted to really show you one more, which I think is the coolest one, next time on Markov processes. Yeah, hi. Hey.